So this week is the last week of basically working with limits. We have a good introduction so far as to what limits are and kind of what they mean and how we're trying to use them. And so by the end of this week's videos, we will have an understanding of how the limit plays its role in working with the derivative in calculus. But for right now, we're going to kind of add to our repertoire or to our catalog of tools that we have for dealing with limits. And I do want to preface this video by saying that personally, I don't really care for teaching this section very much. And it's not that learning how to solve limits or how to approach solving limits is useless. It's just that these particular examples that I'm going to show you are very, very specific cases of, oh, if it just so happens, then do blah thing. And so we are going to focus on basically just looking at some different examples of limits. And we're going to say, okay, like this is how you can approach a particular limit problem of this nature. And so we're going to start off with, something like this. X approaches -1, and we're going to do the limit of, we'll do x squared plus 4x plus 3 over x plus 1. Okay, now with the tools that we have so far, all we know at this point is, well, we're just like, oh, it's a polynomial on top, polynomial on bottom. This is a rational function. I should just be able to try and plug in x is -1, because remember that there are three cases, right? Either our function is continuous, in which case I can just plug in x is -1 and I'll get something, or our function will have maybe a break of some sort at -1, like an asymptote, or there's going to be a hole at -1. And these cases are the cases of what happens when, if you plug something in, you don't get an answer. And it's not too hard to see that if we take x is -1 and we plug it in here, we're going to get a -1 plus 1 in the denominator, which is going to result in a 0. And last time I checked, we are just not allowed to divide by 0. And actually, in the last one of the last videos that we covered on limits, we actually proved why you can't divide by 0. And so this first technique of what the heck do I try and do is very simple, which is we're going to go back all the way to Algebra 2 class, and we're just going to say, look, one technique, one thing you should try. If you see a problem like this, if you see a limit and things didn't work out by plugging it in, you should see if things cancel. Okay, see if things can cancel. Okay, and in this particular case, what I mean is, let's see if I can factor out the numerator, right? If we can factor the numerator, then this limit might end up being solvable. And so we're going to do the limit as x approaches -1, and if we factor out the numerator, we get x plus 3 times x plus 1, and we still have our x plus 1 in the denominator. Now at this point, if you remember your pre-calc 1, you may notice that, oh, so this is not an asymptote, right? There, what kind of discontinuity do we get if it turns out that we can cross this out, right? If we were to ignore just x is -1, right, then we could just cancel this out. And in the instance that I can just ignore a single point and everything works, that means that we have a graph like the one here on the right with just a removable or a point discontinuity. And so here, it's right to be kind of cautious, right? I claim that we can just cancel this out and turn this into the limit as x approaches -1 of x plus 3, and that has an answer of just positive 2. And this should, give you pause. You're like, well, wait, I thought, if I plugged in -1, this is 0. Isn't this doing 0 divided by 0? Isn't that going to be a problem? And the answer is no, because remember that a limit, technically speaking, is not plugging in x is -1. Remember that on this graph, we're looking at a whole bunch of x values, and if this is x equals -1 where that hole is, our job our job is to look at all of the x values that are kind of approaching -1 from the left and all of the x values that are approaching -1 from the right. And we are supposed to look at that and make a conclusion about where we think we're going to end up. And so in this particular problem here, right, when we cancel out x plus 1 and x plus 1, we're doing that because we know that we're looking at all the points except for x is -1, so we don't have to worry about any funny business there. And so if you were to graph this, on a graph, what would this particular function look like here? It's simply just going to be a straight line. It's going to be a line of y is equal to x plus 3, because that's what we would get if things canceled out and we were omitting -1. So we'd have y is equal to x plus 3, so we'd have something that looks like this, right? We have an intercept at 0, 3, but we would have a hole at -1 right here. We'd get a hole, and this coordinate would be -1, comma 2. That's where that hole would happen, because 2 is the value we expect to get as x approaches -1. Okay, fantastic. So that's not too bad, right? It kind of makes some sense. Okay, see if things can cancel, see if we can factor things. And I do want to just reemphasize, right, this entire problem kind of falls apart and maybe is not even solvable for us if I can't factor this, right? If there's a +4 or a +5 or a +6 here at the end, my example is not going to work. Like, I'm very aware of that, and I think the textbook, if you go and read this section, they don't really quite say that. They just give a whole bunch of problems where these techniques always work. But there's going to be way more problems where this particular technique is not going to work, where things aren't just going to magically simplify and cancel. So we're going to try and add even more types of problems to our catalog. And so for the next one, we don't want to be highlighting right now. For this next particular problem, let's do a limit as x approaches. Oh goodness. Let's do as x approaches 0 of x plus 1 squared minus 1 all over x. Okay. And again, this particular one, I already know I'm going to have a problem, because if I try and plug in 0, I'm immediately divided by 0. I don't even need to plug in anything else. I know that I cannot evaluate whatever this function is at 0. And so I'm going to have either some asymptote, either I have an asymptote at x is equal to 0, or I have a hole. Now, one of the things that we just learned about is to try and factor the top. But the top is not exact. I mean, it's kind of factored, right? This is factored, but this, we can't exactly factor this, or maybe not in the way that you and I are maybe thinking about. But the next suggestion that I have is simply going to be to expand things. Okay, expand things. If you don't see anything that's canceling out, and we're gonna have trouble, right? I can't just get rid of this x, and I can't plug in 0. A next natural thing to do would be to have the limit as x approaches 0, and to expand out this little mini hidden quadratic here, right? And so if I FOIL that out, I'm going to get x squared plus 2x plus 1 minus 1 divided by x. And now, if you're paying very close attention, this plus 1 and minus 1 will cancel, and that's going to give us the limit as x approaches 0 of x squared plus 2x divided by x. And at this particular point, again, because we're not technically evaluating this at 0, right? We're not technically doing that. Then I can go ahead and cancel an x out of each of these terms, which is going to give me the limit as x approaches 0 of, just x plus 2 over 1, which is just x plus 2. And now I can evaluate this limit because nothing's bad's going to happen, and I'm going to get 2. Okay, just so happens the same answer as the last question. Weird. But the point being that, whatever shape of this graph is, it's basically saying that if I were to look at it, and it's doing who knows what, that clearly some funny business is going on right here, right? Clearly some funny business is going on right at x equals 0, but I would expect, courtesy of what's happening around this graph at x equals 0, I would expect to be hitting y is equal to 2 at that point. Okay, so this particular example is simply just, all right, if you see something, try and expand things. I mean, it's actually a very common trick when you'll notice 2 videos from now when we tackle the derivative, that doing this method is a very, very, very common trick. The idea is usually that I want to evaluate this thing at 0, but I can't do it because I have, just an x in the denominator. And so we hope that we can rearrange things so that I can get to basically I can get to this point and everything has an x and I can just cancel them all out, and then, my problems are solved. I'm not dividing by 0 anymore. So the last one that we're going to tackle is, again, not my favorite, but here we go. We're just going to do it. So an example might be, let's do the limit as x approaches. Let's just do 0 again. Let's see, what do we want to do? Let's do the square root of x plus 4 minus 2 over 3x. Okay. Now this one, again, looks completely different than the last two that we just tried. There's not really anything to factor anywhere on the top or the bottom. There's nothing to FOIL out either. And so we're going to need a completely different trick. And again, this is more just like, I couldn't even describe this to you. It's like you have to work on a car and you have to loosen a bolt and you're just reaching into your tool bag and trying different, you can't see what the head of the bolt looks like. So you're just trying different things and hoping that one of them works. That's pretty much what this entire section is about. And as an aside, we're actually going to need to remember something from pre-calculus 1, a little well, not really a theorem, but I guess just a little nice property, which is that if you have something like x minus a multiplied by x plus a, right? Something that looks like this. This is the difference of squares formula. So we're actually going to get x squared minus a squared here. And if you don't believe me, you could FOIL this out. We're going to get an x, or it's x squared, a plus an xa, a minus an xa, so those middle ones cancel, and then we're going to get, I'm double counting here, and then we're going to get a minus a squared. So the point being that when I see this particular problem, okay, and I see a square root here, and first and foremost, I'm just like, I don't even like dealing with square roots. A thought could be, and again, this is not going to feel very natural for you. It's not the first thing I would ever think to do. But what we can do is we can identify, hey, look, I have something minus something else. That's kind of like having an x minus an a. And I know that if I were to multiply this thing by an x plus a, right, by the x part plus a, then it's going to result in the first thing squared minus the second thing squared. Why is that interesting? Well, because this first thing is a square root, and I don't like square roots, but if I square a square root, all of a sudden, maybe things are nice and things, the square root goes away and I can start combining like terms and hopefully things work. And so our strategy in this particular problem is going to be to use what we call the conjugate. Use the conjugate. Oops, can I spell? Conjugate. Or, and when I say use, I mean multiply. Multiply the top and bottom by the conjugate. So the conjugate is the fancy name for if I have x minus a, then the conjugate of this thing would be x plus a. And if I had x plus a, the conjugate of something like this is what we would call x minus a. If you want, you can deep dive why that is. For right now, all I'm going to say is, look, we're going to take this particular problem. We have a square root on top. We don't really like that, and we can't do any of our other tricks. So I'm going to multiply the top by the square root of x plus 4, but then I'm going to do a plus 2. And, to make sure that I don't screw anything up and that I keep things all fair, we have to do the same thing on the bottom so that we don't change the problem. But the important thing is here that now I have the first term here, the first term here. I have the second term here and the second term here. But now I have the minus and the plus, and so we get to use the difference of squares thing. And the top is just going to simplify really nicely for us. So the top is just going to simply become this first thing squared, which is just x plus 4, and then minus the second thing squared, which is just going to be 4. Now in the denominator, what do we have? We have 3x times the square root x plus 4 plus 2. Okay, we have something like this. But now you're going to notice that in the top, this plus 4 and minus 4 cancel. And so our limit, our limit now is something a little simpler. We have x over 3x times our conjugate x plus 4 plus 2. And notice that I didn't multiply this all out because what I'm going to appeal to is the fact that I can now cancel out these x's here. And that's going to give me a limit as x approaches 0 of 1 over 3 times the square root of x plus 4 plus 2. And now I can just plug in x, no problem. And if I plug in x is 0 here, I'm going to get square root of 4, which is 2, plus 2, which is 4, times 3, which is 12. And so this limit is finally going to equal 1/12. Now we can actually evaluate this limit. Yeah, and that's it. This is the end of the video. That's it. So, there's going to be some problems in the homework, about this. Me personally, should you be worried about, doing a bunch of these sorts of problems? For me, in my experience doing math and teaching math, I'm going to say that in my opinion, it's not the end all be all of math, especially in a calculus course. There are bigger fish to fry. But I do want to show these things as like, hey, you're going to see some limit problems. And yes, they are going to be very specifically designed and curated. That way, you can use these techniques and actually get some real answers, right? My goal is not to give you limit problems that you can't solve and that you can't evaluate. So you can either, you can either see if things cancel, you can distribute things, see if that helps, and see if using the conjugate helps. Those are going to be the 3 tools that we have. And if none of those 3 things work, the worst case scenario is that we just start plugging in x values that are close to 0, like 0.1 and 0.01 and 0.001, and see if we can just guess what the answer is. But yeah, that's going to do it. I think I'm just going to leave this video here. Short and sweet, 3 examples. Hopefully it was helpful. And in the next one, we're going to tackle one of the more interesting cases that we encounter when we deal with limits.